We're going to start with the concept of titration and specifically on acid-base titration. So titration is nothing more than an experimental technique. It's what we use to analyze concentrations of an unknown species by reacting it with a species of known concentration. The common example that we use for general chemistry is in acid-base reactions, and so that's why it's called acid-base titrations. So in this case, we usually use a burette and an Erlenmeyer flask to do our titration. In the Erlenmeyer flask, we usually put species that we don't know the concentration of, and in the burette, we put the species that we know the concentration of. The one that we put in the flask is called the analyte, and the one we put in the burette is called the titrant. And what we do here is we add enough solutions in the burette, which is the titrant, until the reaction is complete. For the example in the picture, the solution in the flask is the acid, the solution in the burette is the base. So we added enough base in here until the acid and the base are just neutralized stoichiometrically. Now, the word stoichiometrically here is really important to underline. What we mean here is that if the stoichiometry of the acid and the base happens to be 1:1, then if we have 1 mole of acid, we're going to need 1 mole of the base. However, if the stoichiometry is 1 mole of acid to 2 moles of base, if we have 1 mole of the acid, we're going to need to titrate it with 2 moles of the base. A major confusion a lot of times is people would just say that the quantity of the acid and the base have to be equal to each other. It's not quite correct. What's correct is that the quantity have to be stoichiometrically equal. Okay, so it depends on the stoichiometric coefficient. Now, I would point out that another thing that we add to these titration to help us know that we've reached that point is called an indicator. You may remember from our discussion in a prior video that an indicator is a substance that would react with an acid a certain way and it would react with a base a different way, but it usually changes color depending on which one it reacts with, and so that's how we know that we've reached the point where the acid and the base are stoichiometrically equal. That point is what we refer to as the equivalence point for the titration. Now, there's another term called the endpoint, which is almost similar to the equivalence point, but not quite. So the endpoint is actually the point when the indicator changes color. The equivalence point is the point when the quantities of the acid and the base are stoichiometrically equal. So you might think that those two things are the same, but they're not quite. We do try to pick the endpoint to be close to or equal to the equivalence point so that as the indicator changes color, that also tells us that the quantity of acid and base are stoichiometrically equal to each other. We're going to close off this topic on aqueous solution by talking about doing stoichiometric calculations for reactions that happen in aqueous solution. The main thing about stoichiometry is we would need to convert our quantities into number moles of our known and our unknown species. In previous videos, we had talked about how to do that conversion from mass to number moles using our molar mass. Now we're going to talk specifically about the aqueous solution, and the new concept we learn here is molarity. So once we have molarity or molar concentration, we can also convert from volume to number moles using the molarity of that species. And that's just based on the definition of molarity, which is number of moles over volume. So let's take a look at the example problem here, and I'm going to just explain it conceptually how you would do this. So you have a reaction between H2SO4, sulfuric acid, with sodium hydroxide, and the equation is already balanced for you. The question here is how much 0.125 molar NaOH do we need to completely neutralize or react with 0.225 liters of 0.175 molar H2SO4. Now, when we have these type of problems in standard stoichiometry, we would have to convert them to number of moles first. Typically, we're given mass of some kind. We're going to do the same here. We're going to have to convert to number of moles, except that what we're given is volume and molarity. So to convert these to moles, you're going to have to multiply them, because remember, m times v is equal to number of moles. So that's the first step to do. So now once we have the number of moles of H2SO4, we can use our balance equation and the mole-to-mole relationship between the two reactants to calculate the number of moles of NaOH. So that's going to be our step 2. And the last step is to take that number of moles and the molarity of NaOH and use the molarity definition again to convert that to the volume of NaOH. Let's now take a look at a aqueous solution stoichiometry question. Here we are given a reaction between hydrochloric acid and silver nitrate, and we're asked to first write the balance equation and then answer a couple of stoichiometry type questions. So let's start with the balance equation. This obviously requires you to know nomenclature in order to be able to write these reactants. So HCl is hydrochloric acid, silver nitrate is AgNO3. Now, of course, the problem here is what are the products? Here's where you need to remember one of the other concepts we've talked about, which is the types of reactions. And when you have this kind of a reaction, this is a double displacement reaction where you have the pattern of AB plus CD forming AD plus CB. And so we're swapping the cations in this case. So that's what we will do. We would get AgCl and HNO3. And then from there, we need to find out what the states of each of those products is. And to do that, we usually use our solubility rules. And so AgCl, if you check the solubility rules, ends up being a solid. And then HNO3, it's a strong acid, so it's just going to stay aqueous. The last part of it is to balance, but the equation is already balanced as is, so we're good to go here. I'm going to take a look at question B, where it says how many moles of AgCl is produced from 30 milliliters of 0.1 molar HCl. So implicit in that question is the assumption that your silver nitrate must be your excess reactant and your HCl must be your limiting reactant because they don't provide any additional information. To get the number of moles of the product, you need to convert the HCl into number of moles first. So this is where we're going to need to use our molarity definition. Molarity is equal to the number of moles of HCl versus the volume of the solution. And so if we want the number of moles of HCl, then we can see that we can do a cross multiplication, or you can multiply both sides by volume. That would cancel out the one on the right side, resulting in M times V, as I said earlier. So once you have that, then you just take the molarity of HCl that you have, which is 0.1 molar, and then multiply that by the 30 milliliter. Now here's where you want to be a little careful. If you look at the units, molar, of course, means moles per liter. So it's really moles of HCl per liters of solution. And then here we have 30 milliliters. So the liter and the milliliter will not cancel. So that's where you need to convert your milliliter to liter. In this case, we would get 0.03 liter. And that would cancel out, giving us 3 times 10 to the negative 3 moles of HCl. And I should put a few more sig figs here. We can do that at the end. The last question is the number of moles of AgCl would just be the number of moles of HCl times the usual mole to mole ratio between AgCl and HCl. From the balance equation, we have 1 to 1. So it ends up being 3.0 times 10 to the minus 3 moles of AgCl. Let me take a look at the last question. It says here, how many milliliters of 0.1 molar HCl is needed to produce 17 grams of AgCl? So I'm going to erase this a little bit because they kind of switched the question a little bit here. Now they're saying I want to make 17 grams of AgCl and I want to know if my concentration of HCl is 0.1 molar, what's the volume in milliliter? So the way we do this is kind of reversing the steps we did here in the previous problem. We start with the mass of AgCl, so we need to convert the mass of AgCl to the number of moles of AgCl, which is going to be 17 grams divided by the molar mass, which is 143.32 grams per mole. And this ends up giving us this many moles of AgCl. Once we get the number of moles of AgCl, we can use that and the balance equation to calculate the number of moles of HCl, because that's the thing we're interested in. And this ends up being a 1-to-1 stoichiometry. So the answer is going to be identical. Okay, so then the last step is to figure out the actual volume. So for that, you're going to need your molarity definition. So molarity of HCl is equal to the number of moles of HCl over the volume of solution. So if I need to get volume, then it's a bit of algebra. I'm going to have to multiply multiply both sides by volume of solution. When I do that, I end up getting volume of solution times molarity equals number of moles. And then I have to isolate the volume, so I'm going to divide both sides by molarity of HCl. And so what I end up getting is this: volume of solution is equal to number of moles of HCl over the molarity of HCl. The number of moles I already have from my calculation. The molarity is given to us as 0.1 molar, so we would write that down. And remember that 0.1 molar is the same as 0.1 mole per liter. And this is how your units cancel out. And then you have 1 over liter, which just becomes liter. And so your final answer is 1.19 liter of solution. In milliliter, this would be 1.19 times 10 to the third milliliter.